Hi, and welcome back to another LeetCode video. Today we're looking at dynamic programming problems. This time it's a two-dimensional one, LeetCode 62, unique paths. And the problem is as follows. So there's a robot in an M by N grid, and the robot is initially located at the top left corner at grid position 0, 0. And the robot tries to move to the bottom right corner where the finish is. Which is given at the grid m-1 and n-1 coordinates. And the constraint is that the robot can only move either down or to the right, and it can never move up and it can never move to the left. So the question now is, how many different ways are there for the robot to reach the finish, right? You can imagine that it would just go on top row all the way to the right and then just to the bottom. That's one way. You can imagine that it goes the same path, but before reaching the last column, it starts to go down, etc. So let me just copy this example here. And maybe we take this to the drawing board. So we can draw on it. And right, so you can have, like, this could be a path. That could be a path. This could also be, This could also be a path, So, well, how do we count all the number of ways to reach the goal? Well, this problem has a nice property, which is that you can compute the number of ways depending on previous positions that you can go to. So for the first cell, there's one path to reach that cell, and that's just the start. Now, for all of the other cells here, there's exactly one way to reach them, because that's just by going to the right with the robot. I should write the one like this, right? Then no two ways to reach the cell, because we cannot go up and we cannot go left. We can only go right, or we can only go down. Now the same for all the cells in the first column. We can only reach them just by going directly down. So that's the only path to reach them, is going down from the start. Now, how many different ways are there now to reach this cell? Well, we can come from the left neighbor, or we can come from the top. So there are two ways, which is just the sum of these two. Now, how many ways are there to reach this cell? Well, it's however many ways are to reach the top, the cell above, and the cell to the left. That's going to be 3. And so that's going to continue 5, 6, 7. And here it's the same, except now we have 2 ways to reach the cell from above, and 1 way from the left. But it's still the sum of the 3. So 6. So this will be 10. We have a 15 here, 21, and finally we'll have 28 as the result. And as you can see, that's exactly what the result is. So how can we translate this into code? Well, I would say that we have a special case. So if the y coordinate, if we can see this as an xy coordinate system, x and y grows with the number of rows. So if y is equal 0, and the other special case is if x is equal 0, in that case we know that there's only one way to reach the cell, regardless of what the other coordinate is. So I think we should take care of that. And then for all the other cells, we can use the logic, just add the cell above and the cell to the left. So what you see here is the properties that you need to solve a dynamic programming problem, which is you need to have overlapping sub-problems, which is exactly that, where in order to solve the big problem, how many ways to reach the finish, you solve all the smaller sub-problems. How many ways to reach the start? How many ways to reach the cell next to the start, etc. And you compute all of these, we solve all of these little sub-problems, and then you can combine them to come to the real solution. So the overlapping sub-problems is a prerequisite for dynamic programming problems. Right, and so we could create just a matrix like this, and just fill in out all the values. That would give us a n times m space. But really, we only need to keep track of the current row and the row above it, right? When we compute the results for this row, we're not interested in the first row anymore. We only need the results from the row above and from the results that we've written to the row. So we're going to use a technique where we really just store the last row that we've computed in order to compute the next row. And we just iterate with our x across all the cells in those rows. So that'll leave us with an O of, I think, n space, but we still have to iterate over the whole matrix. So it's an O of n times m time complexity. Right, so yeah, so let's jump into writing up the solution. Let me just write the time and space complexity down because we've just talked about this. Time and sorry, n space. Let me just check if m and m, right. Yes, m represents the height. Yes, and n represents the width, right? So, well, what if it's higher than wide? Well, then it would be O of m. Would it? No, the space is correct. If we want to optimize a tiny bit and want the minimum of the two, what we have to do is we just have to check if m is smaller than n. Well, I'm not hitting my keys here. If m is smaller than n, just going to return self, just going to call the same problem and just going to, how do you say, transpose this grid? Because the number of ways doesn't matter whether it's a 3 by 7 grid or a 7 by 3 grid, it's the same. And we just flip this by m. It's just a tiny thing. You don't really have to do that, but it gives us a little tighter upper bound for the space complexity. Right. Okay, cool. So now, well, we have to keep track of the current row. And you can think of it like so that, you know, the row above the first row, you could interpret as those as just zeros, right? Wanted to interpret them as zeros, but you don't have to. However, I'm going to initialize that row with zeros. That's what I'll do. Then we iterate over all of the rows for y in range m. M is our height. And now we create our little temporary array that we're going to fill up while we compute the number of ways to reach a cell in the current row. And the current row meaning temp. And row is going to be the previous row. Maybe I should call them prev and current, like so. Okay, so now we need to iterate over all of the cells in the current row for x in range. Well, this time it's n, right? And what do we do? Well, it depends on what the value of x is. So if y is equal to 0, we know we're in the first row and we know the number of ways is going to be 1, right? Also, if x is 0, if x is equal to 0, we know that the number of ways to reach is also 1. So we could just say if y is 0 or x is equal to 0, number of ways is always going to be 1. Else, well, otherwise, the number of ways is, well, it's our previous row at x, no, sorry, it's the current row at x minus 1. So that would, if we compute, let's say, the value for this cell, current row minus 1, that's this cell, and previous row at x would be the cell above. So current row at x minus 1 plus previous row at x. Right. And then we just update our current row. So current row at position x is ways. Right, and then finally we have to do, well, we have to swap the rows. We have to remember what the current row was for the next iteration. And at the end, all we need to do is return the very last value of the current row. That's all we need to do. And we could also just call this previous. Because what if m was 0? I don't think m can be 0. Not can't, but it could be. And whether return previous or current doesn't matter. They were equal after we exit the loop. And we just return the very last element in there. So let's run this through the tests. And they pass. And if we submit this, it also passes. Right. So that's a very easy way to solve this dynamic programming problem.